IHD is index of hydrogen deficiency. And it can also be called degrees of unsaturation. And it's basically a way to measure how saturated or unsaturated a compound is. And it's used in a variety of ways. So 2 particular uses for the IHD. One is if you have a molecular formula, you can use it to help you determine the structure more easily without having to do a lot of hydrogen atom counting. You can also use it to compare structures to see if they are constitutional isomers. And I'll show you both examples as we move through this information. But first, let's give kind of a more mathematical definition for IHD. It is the sum of the number of rings plus the number of pi bonds in a structure. Okay, and this is the definition we will use most often when we are actually looking at a structure. So just as an example, the structures I already have drawn here, we can go in and we can determine the IHD simply by counting the number of rings and the number of pi bonds and then adding those numbers together. So here, all of these have fully saturated with hydrogen, carbon atoms and other atoms. So there are no pi bonds, there are no rings. So all of these would have an IHD equal to 0 because there are 0 rings and there are 0 pi bonds. Both of these structures here have either 1 pi bond, as in this structure here, or 1 ring. So both of these would have an IHD equal to 1. This compound has 2 pi bonds, so it has an IHD equal to 2. In theory, you could also have a structure with 1 ring and 1 pi bond. You couldn't make 2 rings with only 3 carbon atoms. But the one on the right here, this would be kind of improbable just because it's very high ring strain, and then having a pi bond for one of those is pretty unlikely. So I'm not going to draw that one or utilize that one. So let's take just a minute and look at the relationship between these compounds and the number of carbon atoms. So they all have 3 carbon atoms. So they're all C3. And the ones up here are going to be fully saturated. And we notice here that this particular one has 2 hydrogen atoms for each of the carbon atoms, except for the end carbon atoms need an additional hydrogen atom. So we end up with 8 hydrogen atoms. So this is going to just be a simple saturated hydrocarbon. With no heteroatoms in it. And so there's a little formula we can use when we have a saturated hydrocarbon to determine the number of hydrogen atoms we expect. And it turns out that because we need 2 hydrogen atoms for every carbon in the middle of the chain, and then we need an additional one for each end of the chain, this 2n plus 2 is going to be that formula. And we see here that this propane adheres to that because 3 times 2 is 6 plus 2 is 8. Now, if we look here at the next molecule over, it's an alcohol. It is, in fact, a primary alcohol since the alpha carbon here only has one carbon atom attached to it. And if we go in and we notice how many hydrogen atoms there are here, we actually end up with the same number as we had in the compound to the left. So it turns out when we have an oxygen atom, we're going to have no change in the number of hydrogen atoms. Okay, and that'll be generally true for sulfurs that bond as either sulfides or thiols. For this next molecule over, we again have 3 carbon atoms, but this time we have a chlorine. And notice what happens with the chlorine is that it's basically substituted for one of the hydrogen atoms. And therefore we end up with 1 fewer hydrogen atom for each halogen. And so instead of having 8, we only have 7 here. And this will be true for any halogen. So when we have a halogen, we're going to have -1 hydrogen atom for each halogen present in the structure. For nitrogen here, what's going to happen is because of the way it has 3 bonds, we're going to end up with an extra hydrogen atom for every nitrogen that we have present in the structure. So in this case, we have 3, 4, 5, 6, 7, 8, 9 hydrogen atoms. So that means for every nitrogen atom and every phosphorus that ends up having 3 bonds in a lone pair, we're going to have +1 H atom. These last 2 here, these last 3 here, do have pi bonds. So this would be unsaturated. This would also be unsaturated. This one is going to have only 6 hydrogen atoms. So what we notice is that in adding that pi bond, we're going to lose 2 hydrogen atoms. This compound is also the same molecular formula. So that means these 2 compounds here are constitutional isomers. Because they have the same molecular formula, but they're different structures. They have different connectivity. So notice that for every ring or pi bond, we're going to lose 2 hydrogen atoms. And we see that continue in the structure here, this very last one, where we end up with only 4 hydrogen atoms. So we've lost an additional 2 because there's an additional pi bond. So for each IHD, we're going to lose 2 hydrogen atoms. So because of these patterns, we can come up with a formula, a mathematical formula to determine IHD from a molecular formula. So it's pretty easy to just count rings and pi bonds when we're looking at structures. But where this really gets useful is if we have a molecular formula, we can use IHD to help us more easily draw viable structures. This, along with the concept of functional groups, will really help us. So let's take this, and I'm going to write down the mathematical equation, and I will give this to you on the first quiz, but then you'll need to have it memorized. I admit I tend to not memorize it in the traditional format, and I'll show you how I work through it. And again, whichever method works best for you is the one you should use. So whatever you're comfortable with, whatever you can more easily remember, whatever gets you to the correct answer consistently is what you want to do. So notice that this is the same that we were doing earlier. So this bit gives us the number of hydrogen atoms we would expect for a saturated hydrocarbon with that number of carbon atoms. This is the part that every time we have halogen, it's going to substitute for a hydrogen. So we lose one hydrogen atom for each halogen. The nitrogen we do +1 because we're going to add a hydrogen for every nitrogen. And then this is going to be the number of hydrogen atoms actually in the molecular formula. And so what this math here is going to give us is kind of the number of missing, so to speak, H atoms. And because we lose 2 hydrogen atoms for every ring or pi bond, we're going to need to divide by 2. Okay? So this structure here, let's take this molecular formula and come up with some structures. Since we have 8 hydrogen atoms here, there are going to be a lot of structures we could draw with this particular molecular formula. So I'm going to draw a few of them. You can probably come up with a lot more. I'm not entirely sure exactly how many structures are possible to draw as feasible structures with this. So I'm going to take the 1/2, 2 times 8 plus 2 minus, there's no halogens, there's no nitrogen atoms. Oxygen doesn't affect the number of hydrogen atoms. So then I just need to subtract 14. So 2 times 8 is 16 plus 2 is going to be 18 minus 14 equals 2. Minus 14 equals 4. Divided by 2 equals 2. So the IHD is 2. So that means the sum of the rings plus pi bonds in the structure will equal 2. So that means I can have 2 pi bonds. I could have 2 rings. Or I could have 1 ring plus 1 pi bond. And those pi bonds could be together as a triple bond, or they could be apart as 2 different double bonds somewhere in the structure. So I'm just going to draw a few compounds, but I just want to show you kind of the way I do it without the formula. I mean, technically it is the same as the formula. I guess I don't write out the formula. So again, whatever helps you. So I tend to remember this equation. And so again, it'll be 8 times 2 plus 2. So that'll be 16 plus 2 equals 18. So this is how many hydrogen atoms I expect if I have a saturated hydrocarbon. And I see I only have 14. I don't have any halogen atoms. I don't have any nitrogen atoms, so I'm not going to change anything there. If I did, I would at this point. And then, so that means I have 4 kind of extra hydrogen, or I'm sorry, not 4 extra, 4 missing H atoms. And again, I know I lose 2 hydrogen atoms for every ring or pi bond. So that means my IHD will actually be 2. Okay, so let's draw a few different structures here that might work for this compound. Let me give myself a little more space here. So let me start with 2 rings. Since I have 8 carbon atoms, I could do a 6-membered ring. And then I could do a 5-membered ring with an ether. One thing I forgot to do is analyze here. Since I have an oxygen and I have the potential for at least 1 pi bond, I can have an alcohol, I can have an ether, I could have a ketone, I could have an aldehyde, and I could also, I suppose, have an alkene or an alkyne because of the number of points of unsaturation. So here I have 6 carbon atoms, 1, 2, 8 carbon atoms. I have my 1 oxygen. And because I have 2 rings, the IHD of this is 2. So I should have the right number of hydrogen atoms, but we can go in and double check just to satisfy ourselves. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is in fact C8H14O, and I used the hydrogen atoms to double check myself, but if I'm confident in my calculations, I shouldn't need to do that step. We could also have an alkyne, and then it could have an ether or an alcohol. But then I need a total of 8 carbon atoms. So I've got 1, 2, 3, 4 currently. So 1, 2, 3, 4, 5, 6, 7. I need 1 more. And then I can double check my hydrogen atom count. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that one matches. So let's do one more. I'll make one with an aldehyde present. And maybe I'll put it on a ring. Sorry, this is going to be a ketone, not an aldehyde. So that's 1. Let me fix my little ring here. It doesn't look very good. One, 2, 3, 4, 5 carbon atoms, and so I need 3 more. So I could just do something like that. And since I have a ring plus a pi bond, this should be 14 hydrogen atoms. 5, 6, 7, 8, 1 oxygen atom. So I have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So once again, so all of these compounds here, since they all have the same molecular formula, but the structures are different, they all have an IHD of 2, and these are all constitutional isomers. Because they all have this molecular formula, but they are different structures. They have different connectivity. We would give these compounds different names. Okay, one last thing. Let's look at how we do this for comparing structures as constitutional isomers to make that a little bit faster. So I've already drawn out a few structures here to do this with. We have 1, 2, 3, 4, 5 carbon atoms. We have some number of hydrogen atoms, which I'm going to count later, but I'm going to use IHD first. And then I have 1 nitrogen and 1 oxygen. Okay. Here I have, again, the same elements, but let's check the number of carbon atoms. 1, 2, 3, 4, 5. I have 6. Okay. So this structure, I'll call this one A, this one B, this one C. So since A and B have a different number of carbon atoms, these are not constitutional isomers. Okay, if they had the same number of carbon atoms, but a different number of nitrogen or oxygen atoms, they would also not be constitutional isomers. So let's take a look at, oh wait, first let's write down the IHD of this structure here. So the IHD here of A, we have 2 pi bonds, no rings, so the IHD equals 2. The structure down here, 1, 2, 1, 2, 3, 4, 5. Okay, we've got the right number of carbon atoms. We have a nitrogen and an oxygen, and we have 1 ring here, and we have 1 pi bond. So this also has an IHD of 2. So without doing any more work, I can go ahead and say that A and C are constitutional isomers. Without counting hydrogen atoms. Now, if I'm worried that I didn't do something right and I have time, I can go back and double check. And of course, you can do this without actually drawing out the hydrogen atoms. I'm just drawing them out in case people are still, getting comfortable with the bond line structures. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And then on structure A, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 as well. So we've confirmed that they're constitutional isomers. If I had another structure, say with all the right atoms, one, two, three, four, five. Oh, I've got too many carbon atoms. Let me fix that. One, two, three, four, five, six. Still too many. 1, 2, 3, 4, 5. Okay, C5, H something, and then NO. So I've got the right number of nitrogen atoms, the right number of oxygen atoms. Okay, got the right number of carbon atoms, but my IHD here is only 1. So this is not going to have the right number of hydrogen atoms. So D is not going to be a constitutional isomer of A and C, or of B, because they have different number of carbon atoms. So I'll double check this, but it should be a different number of hydrogen atoms since the IHD is different. All right, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that makes sense because we have one more saturation, I guess, or one fewer ring or pi bonds. So we have 2 more hydrogen atoms than we would expect. Also, just one thing to notice, whenever we have a nitrogen atom, a single one or an odd number of nitrogen atoms, since that's going to add 1 hydrogen atom, we're going to end up with an odd number of hydrogen atoms whenever we have like an odd number of nitrogen atoms. So that's IHD. Again, we want to memorize this formula here. I guess we want to memorize this formula here or somehow have that understanding of what it means when you're looking at the structure. And you also, know when you need to use it. So if you have a molecular formula, you're going to use that mathematical equation to determine the IHD to help you draw a structure. If we're just looking at constitutional isomers, then we're going to use this version of the equation just to help us to compare structures more easily without having to do a lot of drawing out of hydrogen atoms.